Hi, welcome. Today we're going to talk about chemical reactions, and we're going to continue the discussion that we had about synthesis reactions, decompositions, and combustions. So the first thing that we're going to do is we're going to review synthesis reactions and decompositions, which we've covered already in class, but I wanted to make sure that you have a video so it can help you review. All right. Synthesis reactions are reactions in which the reactants are simpler than the products that are going to be made, and therefore we're going to increase in complexity in this type of reactions. The simplest and first type of synthesis reaction that we studied was the synthesis of ionic compounds from their elements. In that case, we start with a metal M and a non-metal X, and we're going to make the ions, and those ions, when we crisscross them, will give us the neutral compound MX, and having whichever subscripts necessary to make that compound neutral. How do we see that? Well, for example, when we have magnesium and oxygen reacting, they will give us magnesium oxide. But how do we know that the formula is MgO? Well, for magnesium, we can see that what we're going to make is the magnesium 2+ ion. For oxygen, we're going to find, and this is particularly important, that the oxygen makes the oxide ion, the O2- ion. It's very important to notice that that ion is monoatomic. We are not taking diatomic oxygen because it's making the ions. And so when we take those two charges, all right, let's see if I can circle that properly. There we go. There. And this one over here. When we crisscross them around, we're going to get that the Mg would come with 2 and the oxygen would come with 2. But because oxygen and magnesium are both being multiplied by 2, we can cross those two out, and we're left over with the Mg formula that we have over here. All right. Other examples include, of course, things like sodium and bromine reacting together to give you sodium bromide, or magnesium and phosphorus reacting together to give you magnesium phosphide. All right. All of those examples, the resulting product is neutral and is the result of the crisscross. So make sure you do that. Make sure that you simplify whenever it's possible. All right. Now, there are other synthesis reactions that we have studied. The synthesis of metal hydroxides is composed by, or is recognized by the reaction between metal oxide and water. And that's going to give you metal hydroxide. And how do you make the metal hydroxide? It's exactly the same thing. You were going to have your metal ion, which you had present in the metal oxide, and you're going to react that with the hydroxide ion, the OH-, and you will crisscross those in order to make the neutral hydroxide compound. So the first example that we have here is when we have sodium oxide reacting with water to give you sodium hydroxide. All right? Now, the formula that I have up there is not balanced. So once we see that, we say, oh, okay, I need to put a 2 here, and now I have 2 sodiums and 2 oxygens and 2 hydrogens in the product side, which is the same thing that we have in the reactants. All right, we get the sodium hydroxide just from the crisscrossing of the Na+ and the OH-. All right, once we get a little bit more complex, when we have higher charges, we can see that for magnesium oxide reacting with water, magnesium oxide we saw just previously, when it reacts with water, we're going to have the crisscross of the OH- and the Mg2+, and that's why we have this 2 over here. All right. Other examples: barium oxide reacting with water to give you barium hydroxide, or scandium oxide reacting with water to give you scandium hydroxide. Very similar to this type of compounds is going to be the synthesis of oxoacids. And in the synthesis of oxoacids, we have a non-metal oxide reacting with water to give you the oxoacid. Now, the oxoacid has this interesting little formula here, all right, the HXO formula, and it's just a way in which we write the oxo acids. It is just the hydrogen, however many hydrogens we had in the reactant, the non-metal, however many non-metals we had, and all the oxygens in the reactants. We put them all together. All right. So if we look at our example, we have sulfur trioxide reacting with water. We recognize that sulfur is a non-metal, and therefore we are not going to do the hydroxides, but we're going to do instead the oxo acid. We're going to take, oh, okay, well, let's see. How many hydrogens do I have here? I have 2 hydrogens, so I put 2 hydrogens. I have only 1 sulfur, so I put 1 sulfur, and then I have 3 plus 1 oxygens. I put 4 oxygens. It is as simple as that. You just have to follow the same pattern every time. H, non-metal, oxygen. All right? It's just as simple as that. Now, you can have more complex oxides, such as the oxide of chlorine 5. All right? And let's look at that. If we have chlorine 5 oxide and water, and you can see that over here, what you can get is something that looks like this. When you put it all together, you have H2, Cl2, and O6. But you hopefully can notice that the H2, the Cl2, and the O6 can all be simplified by dividing by 2, and so I can actually get this compound that would be HClO3, and that's what I've made over here. Notice that to keep this balanced, I have put a 2, so we actually have 2 of the chloric acid that is being produced. All right, that keeps us with having the same number of hydrogens, chlorines, and oxygens on both sides of the reaction. All right, there are also other examples that we can see. We have carbon dioxide reacting with water to give us carbonic acid. Carbonic acid is in your sodas, and that's actually what, when it decomposes, gives soda the fizziness that it has. All right, it's carbon dioxide coming out. All right. Similarly, you can also have the phosphorus 5 oxide dimer, which we have here. And in this particular case, instead of reacting it with just 1 water, we're going to react it with 6 waters. And it gives us 4 molecules of phosphoric acid. If we only initially counted the number of hydrogens, if we look at that, we have a total of 12 hydrogens to begin with. We have 4 phosphorus, and we have 16 oxygens. And so each one of those numbers is divisible by 4, and that's why, again, we have that 4 there and the simplified formula for phosphoric acid. All right, so that's should be straightforward and something that we've worked on before. Now, if we look at the decomposition reactions, we also looked at several decomposition reactions. Decomposition reactions, we're breaking bonds and we're making simpler species than the reactants. All right, because we're breaking bonds, the decompositions that we're going to be studying are endothermic because they require energy to come into the reaction in order to break those bonds. All right, and that's again a little bit of a review for us. Depending on the type of energy that you have, decompositions can be classified as electrolysis, photolysis, thermolysis. There are a few more, but these are the ones that we're going to see at this level. And in particular, we are going to study thermolysis, right? And the ones that we studied 3 different types of thermolysis. We studied the thermolysis or decomposition of carbonates and the decomposition of sulfides. And those are exemplified here, all right? In this particular case, in the first case, we have the carbonate, all right? And when it breaks down, it gives you the metal oxide, and it gives you carbon dioxide. Very similar if you have a metal sulfite. Notice that it's a sulfite, it's an SO3. It also gives you metal oxide, but in this case it gives you sulfur dioxide. They're identical reactions, all right? Only the difference is whether we're using sulfur or carbon as our non-metal. All right, and so it breaks down, and the products that you're going to get are the carbon dioxide or the sulfur dioxide and the metal oxide. And you have to remember to use the crisscross for the metal oxides. You cannot just put elements together, you have to put them so they actually give you the proper formula. All right, so we have a couple of examples down here. We have calcium carbonate breaking down to calcium oxide and carbon dioxide. And how do we know that it's CaO? Because calcium, all right, is Ca2+, and oxygen is O2 negative. And so when we crisscross that, the 2's can cancel out, and we get our simplified version over here. Sodium sulfite reacts to give you sodium oxide and sulfur dioxide. Again, sodium Na+, O2 negative. When we crisscross, we get this neutral compound. We have to have two sodiums to neutralize the oxygen. And finally, aluminum carbonate. When we heat that up as well, it will give us the aluminum oxide, and in this particular case, 3 molecules of carbon dioxide, because we need to keep the reaction balanced, so we actually have all the carbons that we had originally. There's 3 carbons, we need to have 3 carbon dioxides. All right, so that is a straightforward review of what we have done. In addition, we also looked at the thermolysis of chlorate salts. Again, chlorates look very similar to carbonates and to sulfites because we also have that 3 oxygens there, but this is with chlorine. I'm separating this one because instead of giving you an oxide, it gives you a metal chloride as a product and then oxygen. All right, so it releases oxygen gas. This is actually a nice reaction. If you want to have produce oxygen gas quickly, you just heat up a chlorate and it will release its oxygen. All right, and so again, you have to remember that the metal chloride that you get is the product of a crisscrossing. All right, so if we have potassium chlorate, it decomposes to give us potassium chloride and oxygen. And you do need to make sure that you keep your reaction balanced. All right, if we do instead magnesium chlorate, notice that we get MgCl2, magnesium chloride, and the 2 is coming again from the crisscrossing of the magnesium 2+ ion and the chloride ion, which is -1. All right, so keep this in mind. And now we're going to look very briefly at our new material, combustion reactions. Combustion reactions are straightforward. It is when you're burning a fuel in the presence of oxygen, all right, and this is going to release large amounts of energy. For this class, we're going to limit ourselves to using fuels that are made out of carbon, hydrogens, and in some occasions they also contain oxygen in the fuel. All right, 2 examples that we have. If we have methane gas, all right, CH4, it reacts with oxygen to give us carbon dioxide and water. All right, this always, of course, releases heat. This is a compound that we use for cooking. All right, if we have ethanol, all right, CH3, CH2OH, it also reacts with oxygen to give us carbon dioxide and water. So in all of these products, all right, in all of these fuels that we're going to study in our class, we're going to see that the only products that you're going to get are carbon dioxide and water, because we're looking at complete combustions. If this was not so, if it was not a complete combustion, we could get carbon monoxide, we could get carbon particles, but we're not going to worry about that at this level. All right. Again, combustions always release energy. They're highly what is called exothermic, and that's why we can use them in our power plants, in our car engines, and we use them to cook with. So definitely a great source of energy. The one important thing that you do need to remember is that you need to keep your reactions balanced. So for example, if we come and have the combustion of hexane right over here with oxygen, well, there are 6 carbons to begin with, And so if we look at that, we would have to put a 6 over here. Now we have 6 carbons. There are also two hydrogens over here. There are 14 hydrogens over here. I need to put a 7. And that gives me that I have 12 oxygens plus 7 is 19 to the 2 oxygens that I have over there. How do I make 19 and 2 equal to each other? I could theoretically multiply this by 19 halves, but that's a little bit weird. We like to use integers when we are balancing. So what I do is I come and I multiply the entire reaction by 2. And so what I get is 2C6H14 plus 19 oxygens is going to give me 12 carbon dioxides and 14 waters. All right, plus of course a lot of energy being released. So please remember that you need to make sure that reactions are nice and balanced. Okay, so for next class, try to complete the following reactions, all right, and make sure that your answers are also balanced. All right, see you in class and have a lovely time. Until next time, bye.